Welcome back to this third video on the software communication architecture for the design and development of embedded systems. I'm Claude Belil from Viavi Solutions. In the previous sessions, we talked about the ever-increasing role of computers and embedded systems in all aspects of our life, be it with the home automation solutions, in our cars with the adaptive cruise control, the aids and navigations and drive, the radar, the ABS, the lane departure, the anti-pollutions, in telecommunication systems, or in test equipment. We covered the complexity of those computers that we call heterogeneous embedded and distributed systems, or HEDS, due to their composite nature of having multiple processors, different operating system distributed over multiple cards or units. We mentioned that software is a major element of the development cost. Over 60% of the total cost is due to software. And therefore it is imperative to streamline its development to minimize the cost and accelerate the development cycle, i.e. reduce time to market. A key element for this was the software architecture. Too often, the software is still written for the hardware platform being developed. Software is coded specific to the processor being used, to the operating systems, or to the hardware configuration. One can easily see that if there's a modifications of the hardware platform due to improvement or simply obsolescence, the software would also need to be modified, increasing the cost and delaying the release. Over time, multiple software architectures have been proposed and are still in use, but most will target specific domains or require specific hardware configuration. The software communication architecture, or the SCA for short, however, has been developed by the international community to be truly domain and platform agnostic. That is applicable to any type of embedded systems, particularly those composed of multiple types of processors with a distributed configurations. In this sessions, we'll go a little bit more into details on what is the SCA. So in the last session, we introduced the SCA as a methodology to develop software applications by components for heterogeneous systems, promoting software reuse and portability. It was a framework to deploy, interconnect, and control any software components, your own or some from third parties. It is platform agnostic, and it's also domain agnostic. It's all about software components. From a high-level perspective, the SCA can be described as a component-based development approach, a CBD. Much like a computer board is composed of hardware components like processors, resistors, capacitors, electrical wires that can be purchased as single unit and soldered on a board. The SCA promotes the same paradigm with software. The software program becomes a collection of software components that are assembled to execute the code. Each software component is designed to execute a specific task and are not really meant to be modified nor adapted for different systems. They're black boxes to be used as is, same as resistors, capacitors, and processors on a hardware board. You could even think of buying those software components from a catalog or a library of components. In the wireless communication domain, those software components would represent a filter, error correction code, modulator, op converter, interpolator. It is by assembling these components and connecting them together that you create the waveform application. In addition to this signal processing element, there are other types of software components that represent the hardware element or are proxy for them, such that the audio device that would represent a microphone and a speaker, an RF device representing the RF front end, an Ethernet device representing the Ethernet port. Those devices define the platform. As mentioned, the software components are designed and implemented as black boxes and could be ordered from a catalog, each having a spec sheet describing the behavior of the component, what it does, a descriptions of the algorithms. Is it a filter, modulator, error correction code? The configuration properties, how to parameterize them, what properties can be changed. Example, for a filter, it can be the type of filter, its bandwidth, its roll-off, or the number of taps. The interfaces, does the component take integers, float, complex as input, and what does it produces on the output? The requirement, what does it need to run properly, the number of instructions per second, MIPS, the memory requirements. You pick the components you need to design your applications. From a source code point of view, those components should all be platform agnostic, i.e. you should not have to modify the source code to run them on an x86, an ARM, or PowerPC running Linux, VxWorks, or QNX. The SCA defines three types of software components. Those components associated with the SCA core framework itself, managing the life cycle of the software on the platform, i.e. loading the components on the platform, connecting them, configuring, start, stop, remove. The application components, those that are really define the system, those containing the signal processing, defining the behavior of the SDS. And finally, the platform components that are proxy to the platform device, such as the audio port, the Ethernet port, the transceiver, or the platform services, such as the vocoder and timing unit. So what is a software component? As we said, it is a self-contained block, a black box, that executes a specific function, be it related to the applications or to the platform, as we saw in the previous slide. To make it platform agnostic and reusable over different projects, the component is built into two main parts. The outer shelf, that speaks the SCA language, and is used for the life cycle of the component to load, configure, start, stop the component, and interact with it via the I/O or the command ports. To the outsider, this is all that is important. The outer shelf is governed by the SCA specifications, and as we will see later, can be auto-generated with proper software tools. And an inner shelf that contains the business logic or the actual signal processing that will execute. If it is an application-related component, then it could perform signal modulations or a cruise control algorithms or a target detector algorithm. This is where the company intellectual property resides. If the component represents a platform device or service, then it provides the adaptations from the SCA world to the platform-specific world. We will get back to this on a later slide. Here's an example of a model for a software component design with SCA Architect, a commercial SCA modeling tool offered by Viavi. Similar to a hardware chip, the name of the component usually relates to its function, as shown here. An automatic gain control. It could have been an FM modulator, an FIR filter, or a Viterbi decoder. The I/O ports are shown as white or black squares, and the command ports as the lollipops. The properties, or configurable parameters, are listed. The operating environment for which the component is compatible is also provided. There could be multiple environments available. It is the SCA core framework that will decide which one to use depending on the platform configurations. We will see later in a video how to create a component using the tool. Once a design is done, all of the SCA artifacts or the component outer shelf can be automatically generated. No need to really understand the programming details of the SCA. They're generated for you. You should now focus on the behavior or the signal processing algorithms. Here is an example of the code generated by the tool. And you see sections where the tool says, insert your code here. This is where you would insert your own business logic defining what the component will do. In a later video, we will create one such component. Here are two other examples of SCA models for application components used in wireless communication systems, a convolution encoder and a QAM modulator. You see that they both have one input, the white dots, and one output, the top black dots, and one log port. But they have different parameters. The FEC shows configuration modes currently set by default to rate 1/2 constraint length 7, and the QAM modulator is set to default to a 4 QAM, or basically a QPSK modulator. And an example of an SCA model for a platform component using wireless communication applications, namely a component that would represent an audio device, i.e. a microphone or a speaker. We will talk a bit more about the device in the later slides, but I wanted to point out here that the business logic of this components is a bit different from the business logic of an application component. We said that for the application component, the business logic to insert in the component defines the signal processing to be executed by the component. For a platform component, the business logic refers more to the API that must be called to interact with those devices or services. And that business logic is platform specific. Here we show an audio device, i.e. a microphone and a speaker. This device makes use of a pulse audio driver, but it could also have been built with ALSA or pipe-wire drivers. As said, this becomes a platform specific. And here's a more complex device, one representing the RF transceiver. As you can see, it has a lot more properties or configurable parameters as defined by the transceiver device specifications provided by the Wireless Innovation Forum. I won't go into the details of these properties, don't worry. It is just to show that as a designer, you have the options of putting as many properties as required. Here again, the business logic that must be inserted inside the component is to interface with the platform hardware using the RF transceiver specific APIs. Just like the print command on your PC that connects the specific printer driver. For the SCA, the RF transceiver is like the printer, and the RF transceiver device is an encapsulation of the transceiver drivers. The applications need not to know which transceiver is used. For the application, all transceivers are the same. Similar to hardware components that you can pick from a catalog, a library of software components could be built. In fact, the VIAVI SCA suite offers such a library, the SCA DSP Toolbox for wireless communication applications. Here's a list of some of the components in that toolbox. They can be dragged and dropped on the design canvas to start creating applications. And the nice thing about the constructions of these components with an inner and outer shelf is that if you have a better business logic than what is proposed by the toolbox, you can simply replace the inner shelf with your own business logic. Similarly, for the platform-related components, the devices and services, a number of standard components have been defined for wireless communication systems. Here's a list of those devices and services for which there's a specification. As mentioned before, the platform component role is to make the interface between the SCA generic world to the platform hardware. So on one side, they must speak the SCA language, but on the other side, they must speak the platform language. This is shown here on the slide. On one side, the SCA device are the standard APIs mandated by the SCA specifications to provide interoperability and portability. But on the other side is proprietary code to connect to the actual hardware. So the applications will only see the SCA APIs, while the business logic of the device and services will support the hardware. Therefore, for a device and service, the inner shelf of the components will often need to be adapted to the platform. This is not always the case, but will often be. For example, an Ethernet or a serial device or an audio device may not need to be adapted, but something like a transceiver device would most likely need to be adapted to the hardware. In this video, we covered the basic of the SCA, a component-based design methodology for software-defined systems promoting platform independence and software reuse. In the next video, we'll demonstrate how, using proper software tools, NSC applications can be quickly put together by assembling just software components. We will be back after the demo with a closer look at the inside of the SCA specifications. We'll see how it works, what are the main constituents of the core framework responsible for the life cycle of the applications. We will touch on the main responsibilities of the application developers and platform developers. So, see you soon.